Welcome everyone. This is the first video in the series of linear differential equation, and in this video I am going to talk about these topics, so you can quickly look at the topics that I am going to discuss. There are multiple topics that will be discussed here, so this will be a long video. Watch till the very end. So let's start. First of all, what is the definition, or how does a linear differential equation look like? So it looks like that a naught x, nth order derivative of y with respect to x. I hope you are clear about this notation, that if I differentiate y with respect to x, we write dy by dx. This is the first order derivative. If I differentiate it again, I write d2y by dx square. Second order derivative, d3y by dx cube. Third order derivative, and so on. If I am writing dny by dxn, this means that I have differentiated y with respect to x n number of time. So in a linear differential equation, this is the highest order derivative, means we have differentiated it n times. This is the next order derivative, means n minus 1th order derivative, and in the left hand side we have the different derivatives of y and the y term, and in the right hand side we have a function of x. So here this a naught x, this a1 x, and all these are functions of x, right? So I can write it that here the a naught x, a1 x, a2 x, and all other coefficient up to an x along with the right hand side, these are the function of what? These are the function of x only, right? And a naught x, the coefficient of highest order term, a naught x is not equal to 0. So this is how the linear differential equation will look like. In case if the right hand side rx is equal to 0, then we call it as a homogeneous linear differential equation. If rx is not equal to 0, then we call it as a non-homogeneous linear differential equation. So let us look at some of the example and identify that whether these are the linear differential equation. So if you look at this differential equation, first of all, you should not get confused with the dash term here. It is also known as y double prime. So here y double prime is just a notation for d2y by dx square. Means if I am writing 2 prime, means 2 dash means second order derivative. If I write y3 dash, this will represent the third order derivative of y with respect to x. If I write y4, this will represent the fourth order derivative of y with respect to x. So this is a linear differential equation. If I just look at the first one, what are the coefficient? Coefficient a naught x is 1, a2x is 4, a3x is equal to 3, and the right hand side, I just made one small mistake, that I told a naught x, so let me call it a1x and let me call it a2x. So and rx is equal to x square e to the power 3x. So you can see that all these are function of x only. The constant term can also be considered as a function of x, right? So this is a linear differential equation. Similarly, if you look at this example, this is a linear differential equation of order 2. Here if you look at the third example, here the coefficients are a naught x is x square, a1x is x, and a2x is x square minus 4. And what is the right hand side? Right hand side rx is equal to 0. So this is a homogeneous linear differential equation, right? And in this case, the order of the differential equation is 2. So all these are example of the first, second, third, fourth. All these are example of second order linear differential equation. When I say the linear differential equation, means its degree is 1. So the linear differential equation by its very nature is of degree 1. That is why we are using the term linear differential equation. Okay. I am going to write some examples of non-linear differential equations so that you understand that what is the difference. So suppose I write one example, that x square y double dash plus 2xy y dash plus x square y is equal to sine x. So this is an example of a non-linear differential equation, because you see that here y double dash term is coming, with that x square is coming, no problem. So there is no problem with this term. But if you look at this term, there is a problem here. What is the problem here? That with y dash we have the term of y, which should not be there, because the y dash term should come with only the function of x, but because of this y term, this is not a linear differential equation, right? Suppose I write some more examples. Suppose I write y double dash plus 7xy plus 7xy dash plus y is equal to suppose I write x square y. So this is also not a linear differential equation, because in the right hand side we should have a function of x only, but here we have a function of x and y term is also present, so this is also not linear, right? If I write some more examples, suppose I write one more example, that I write x square y double dash plus 7xy dash plus 3y is equal to 0. So this is a non-linear differential equation, because you can see that with y double dash we have a term of y which should not be present. So if I remove this term of y, now it becomes linear, right? So it is very important to identify the equation correctly, and also important to note that whether the differential equation is homogeneous or non-homogeneous. There is one more categorization which we can quickly do, that if you look at this differential equation, the first and second one, here in the left hand side the coefficients are 1, 4 and 3, all are constant. For this also the coefficient is 1, 2 and 1, so these are all constant. So these two differential equation are a differential equation with constant coefficient. But if you take this example, here the coefficients are x square x square minus 4, so this is a differential equation with variable coefficient. If you look at the last example, this is also a linear differential equation, because it can be written as x into y dash is equal to 3y, which in turn can further be written as xy dash minus 3y is equal to 0. So this is an example of a linear differential equation which is homogeneous, because the right hand side is 0, and this is a differential equation with variable coefficient, because the coefficients are x and minus 3. So if one of the coefficient is a variable, then the differential equation becomes a differential equation with variable coefficient. Okay, fine. Now this is a theorem, so don't get intimidated by this long statement. I will explain it, just listen it very carefully. So if the functions a0x, a1x, anx and rx are continuous over an interval I, and a0x is not equal to 0 on I, then there exists a unique solution to the initial value problem. So if you look at this expression, this basically represents a linear differential equation, right, of order n. Here the power n represents the nth order derivative, and these are the conditions which are given. So if you look at this condition, they all are defined at one point, that is x0 and x0, means they are all conditions at just one single point. So that is why this is called the initial value problem. I will explain about initial value problem and boundary value problem later also. Just consider this, that these are the n conditions. So there is a condition that this initial value problem will have a unique solution. And what is the condition? The condition is that all these coefficient, all these coefficients like a0x, a1x, a2x up to anx, these are all continuous on the interval I, like coefficient of highest order term, the second highest order term up to the last term, that is anx, and the right hand side, all of them should be continuous over the interval I, and a0x should not be also equal to 0 in that interval, right? A0x should not be equal to 0, right? So if both the conditions are satisfied, then this theorem guarantees that there will exist a unique solution. This theorem does not tell you that how to solve the linear differential equation. It simply tells you that whether the unique solution will exist or not, right? So you can just read this carefully. that this theorem does not give us procedure to find the solution but guarantees that there exists a unique solution if the condition stated in the theorem are satisfied. And what are the conditions stated? That all the coefficients a0x, a1x up to anx should be continuous on the interval I, and in that interval a0x should not be equal to 0. If the conditions of the theorem are satisfied, then the differential equation is said to be the normal on I, and a point x0 in I is called an ordinary point or regular point of the differential equation. Now moving forward, I am going to take many examples to understand it, and if you have reached till here, I hope you will understand the things better now. So now this kind of questions are important and usually asked in exam also. So the question is that find the interval on which the following differential equations are normal. So we have to find the interval in which the differential equation are normal. So how to solve this kind of problem? So as I told you that if you look at this, this is a linear differential equation, and if I consider the first part here, what is a0x? a0x is 1 minus x square, the highest order term coefficient. What is a1x? So a1x is minus 2x. What is a2x? So a2x is n into n plus 1. And what is rx? So rx is equal to 0. So as far as continuity of this function is concerned, these are everywhere continuous function. We all know a result that polynomial function, and this is an important result, you should remember that polynomial function and constant functions are everywhere continuous. Functions are everywhere continuous, right? So you can keep this result in mind because it will be very useful. So if you look at this, this is basically a polynomial of degree 2. 1 minus x square can also be seen as minus x square plus 1. So this is a polynomial of degree 2. This is a polynomial of degree 1. This is a constant term n into n plus 1 because n is an integer, and right hand side is also equal to 0, which is a constant. So the first requirement is that all these functions are continuous in the interval minus infinity to infinity. But what is the second requirement? That a0x should not be equal to 0. So a0x is what? a0x is 1 minus x square. So this implies that 1 minus x square should not be equal to 0. So 1 minus x square should not be equal to 0 means x should not be equal to minus 1 and 1. So in that interval, the differential equation will be normal, which does not contain these 2 points. So what is the interval? The interval is that it is continuous everywhere on the set of real number from minus infinity to infinity, but these 2 points like minus 1 and 1 should not be included because this is not satisfying the requirement that a0x should not be equal to 0. So if I exclude these 2 points, the interval can be written as r minus minus 1 and 1 set of real number, but usually in our course we don't write it like this. We can write the interval like minus infinity to minus 1. At 1 it is open, and union minus 1 to 1 and union 1 to infinity. So this differential equation is normal in any of the sub interval of this interval, and what I am going to speak is important because this thing that they can exploit in asking MCQ question. So this differential equation is normal in any of the interval which does not contain minus 1 and 1. So if I take an interval like 2 comma 73, so in this interval 1 or minus 1, both of them are not present, so the differential equation is normal in this interval. So basically the idea is that differential equation will be normal in any of the interval, any of the sub interval which is contained in this, means this is the largest possible interval in which the differential equation is normal, right? So but if I take any interval which contains minus 1 and 1, suppose for example I take an interval like 0 to 23, So in 0 to 23, 1 is contained here. So in this interval, the differential equation will not be normal. So the differential equation will be normal in those interval which does not contain the point -1, 1. I hope up to this it is clear. So let me solve the next problem also. So if you look at this next problem, you can see that what is a naught x? A naught x is x square. What is a1x? A1x is x. And what is a2x? A2x is n square minus x square. And what is rx? So rx is equal to 0. So this is a polynomial continuous in interval minus infinity to infinity. This is polynomial continuous in minus infinity to infinity. This is polynomial continuous in minus infinity to infinity. This is a constant function, so continuous in minus infinity to infinity. All these coefficients along with the right hand side are continuous everywhere. There is no problem with that. But the second requirement is that a naught x should not be equal to 0. Means x square should not be equal to 0. Means x should not be equal to 0. So I have to take that interval which does not contain 0. So that interval will be minus infinity to 0 union 0 to infinity. So in this interval 0 is not included, so the differential equation is normal in this interval or any sub interval of this interval. So for example, if I take this question and I ask you that this differential equation is not normal, I am highlighting this, not normal, and suppose I give you the options like 2 to 23, first option. Second option I give minus infinity to minus 1. Third option I give suppose minus infinity to 0. And fourth option I give 5 to 23. So the differential equation is not normal in which interval? You can clearly see that this does not contain 0, so it is normal in this interval. This also does not contain 0, so it is normal in this also. This also does not contain 0, but this interval contains 0 because at 0 we have closed the interval. So this differential equation is not normal in this interval. Okay. So I think this question I already have taken. They have written the same. So moving to the next. Now look at this example number C here. So if you look at the example number C, what is a naught x? A naught x is under root x. What is a1x? A1x is 6x. What is a2x? A2x is 15. And what is the right hand side? The right hand side is ln x to the power 4 minus 256. So this is a polynomial. It is continuous in minus infinity to infinity. This is a constant function, so it is continuous in minus infinity to infinity. So these two functions have no problem, but this function is not everywhere continuous because it is a square root of x. So for this to be defined, the x should be greater than or equal to 0. So we can't take the negative value of x. And what about this? We know that for log x to be defined, x should be greater than 0. So for this right hand side to be defined, x to the power 4 minus 256 to be greater than 0, and this is known as an inequality, and I hope you all know how to solve an inequality. I am going to explain it. So x to the power 4 minus 256 can be written as x square plus 16 into x square minus 16, and this is greater than 0. But we all know that x square plus 16 is always positive. This is always greater than 0. So this implies what? That I can divide the inequality in both sides by x square plus 16. So what I should get is that x square minus 16 should be greater than 0. And this is a standard practice, that if you have a positive factor, you can cancel it from both the sides. Now we have x square minus 16, which can be further factorized in x minus 4 into x plus 4, and this should be greater than 0. So for this to be greater than 0, what value of x can be taken? So you know that if you equate them to 0, you will get the roots, that is minus 4 and 4. and it will be positive in the extreme right, like it will be positive in right of 4, and then the sign changed alternatively, so it will be negative in -4 to 4 and positive in the left of -4. So for this Rx to be continuous, that x should lie in the interval -infinity to -4 and 4 to infinity, right? But there is one more thing that we need to look at, one more thing, that a naught x should also not be equal to 0. So this implies that under root x should not be equal to 0. So this implies that x should not be equal to 0. So now we have all the conditions. So what is the common interval in which all the coefficients are continuous and the right hand side and the highest order coefficient is not equal to 0 and right hand side is also continuous? So it is saying that we have to take x greater than or equal to 0, but this is saying that x should not be equal to 0, means I need to take x greater than 0. But here they are saying that x can be taken less than -4, and here it is x greater than 0, so means I can't take x less than -4. So only common interval that I can take is 4 to infinity. I hope you understood this. Let me explain again. The situation is that we have a point -4, we have a point 0, and we have a point 4. These two are saying that you can take any value of x because they are continuous in -infinity to infinity. But the right hand side is suggesting that either you can take x greater than 4 or less than -4. A naught x is suggesting that you can take x greater than 0 in the right of 0. Means what is the common part? The common part is that I can take x greater than 4, and that will be the interval in which this differential equation will be normal. So the correct answer is that find the interval in which this differential equation is normal. So the interval is 4 to infinity. I hope up to this there is no doubt. Now let us quickly take few more problem. So if I look at this, what is a naught x? A naught x is 1 plus x square. What is a1x? A1x is 2x. What is a2x? So a2x is the coefficient of y, no coefficient, so 1. And what is the right hand side? That is equal to 0. So it is polynomial continuous in -infinity to infinity. This is polynomial continuous in -infinity to infinity. These two are constant, so both of them are continuous in -infinity to +infinity. But a naught x should not be equal to 0. So a naught x should not be equal to 0 means what? That here clearly 1 plus x square is never equal to 0. No, so this is like for no value of x, for no value of x, 1 plus x square is equal to 0, right? Means we do not have to exclude any point. So this differential equation is normal in the whole interval, that is -infinity to infinity, because 1 plus x square can never be equal to 0, right? Let us take the last problem. So here what is a naught x? A naught x is x into 1 minus x. What is a1x? So a1x is minus 3x. And what is a2x? A2x is minus 1. And what is the right hand side? The right hand side is equal to 0. So polynomial everywhere continuous, polynomial everywhere continuous, constant and constant. So all these functions are continuous in the interval -infinity to infinity. But what is the requirement? The requirement is that a naught x should not be equal to 0. So if I put x into 1 minus x not equal to 0 means what? That x should not be equal to 0 and x should not be equal to 1, because if you equate that, if x 0 then this will become 0, if x is 1 then this will also become 0. So x can't be 0 or 1, means from the set of real number I have to include the exclude the point 0 and 1. So what will be the interval? The interval will be -infinity to 0, 0 excluded, then we take the interval 0 to 1, so 1 is also excluded, and then we take 1 to infinity. So this is the interval in which this differential equation is normal, or any sub interval of this interval also the differential equation will be normal. Okay, so this is the first important concept. Next important thing is that linear combination of solution. We have not discussed about how to find the solution of it. In the next video I will talk about how to solve linear differential equation of a special type, but there are certain things which we should know. So one of the thing is that what do you mean by the linear combination of the solution? So if y1x and here it should be y2, y2x and ymx are m solution of a linear homogeneous equation, and this I am highlighting, and this is how the linear homogeneous equation will look like. The right hand side will be equal to 0 on an interval I. Then the linear combination of this solution is written as what? You have studied linear combination earlier also. The linear combination is written like c1 into y1x plus c2 into y2x plus up to cn into ynx, right, where this c1, c2, cm are constant, is also a solution of the above equation. So what this result is basically saying, that I am going to explain through this example. So listen this example very carefully, otherwise you will not follow the concept. So the concept that they are trying to highlight, that suppose there is a differential equation, that is y double dash minus y is equal to 0, and I hope you understand this, that this is nothing but another way of writing the differential equation, that is d2y by dx square minus y is equal to 0, right? So they are saying that this one, there is a function e to the power minus x and another function that is e to the power x is there, and their linear combination, that is c1 into e to the power x and c2 into e to the power x are solution of this homogeneous equation. So first of all, suppose I take y is equal to e to the power minus x, and I want to show that y is equal to e to the power minus x is a solution of this equation. So by that what I mean? By that I mean that if I take y is equal to e to the power minus x, this will satisfy this equation. So let us check. We require y double dash means second order derivative of y. So if I differentiate it once, means if I write y dash, it will be minus e to the power minus x. And if I differentiate it again, y double dash, I will get what? This minus minus will become plus, so I will get e to the power minus x. So you can see that y double dash minus y is nothing but e to the power minus x minus e to the power minus x. It is equal to 0. Means y is equal to e to the power minus x is a solution of this homogeneous linear differential equation, because this is satisfying the equation. Similarly, if I take y is equal to e to the power x, it will also satisfy it, because if I find y dash, this is e to the power x and y double dash is also e to the power x. Okay, so if you put it in this equation, what is y double dash? Y double dash is e to the power x, and what is y? Y is e to the power x, so e to the power x minus e to the power x is equal to 0. So we have noted that y is equal to e to the power minus x is a solution, and y is equal to e to the power x is also a solution. So this result is saying that if y is equal to e to the power minus x is a solution and y is equal to e to the power x is a solution, then their linear combination means, what is their linear combination? Their linear combination will be c1 e to the power minus x plus c2 e to the power x. This will also be a solution of this homogeneous linear differential equation. So can we verify this? That suppose I take this is a solution, means I take y is equal to this. So if this is a solution, means this should satisfy this. So if y is equal to this, what is y dash? Y dash is, if I differentiate this whole thing, I will get minus c1 e to the power minus x plus c2 e to the power x, and then I will find y double dash. So what will be y double dash? This minus minus will become plus c1 e to the power minus x plus c2 e to the power x. Now it is very obvious that if I write y double dash minus y, so what is y double dash? This whole thing. And what is y? This y is this whole thing. So both are same. So y double dash minus y will become 0. So we have just proved the very interesting or important result, that if we have different solution of a homogeneous linear differential equation, then its linear combination is also a solution. And I hope by linear combination you understand that if we have suppose n functions, suppose the functions are like f1x, f2x or f3x, suppose I take 3 functions example, then if I write something like c1 f1x plus c2 into f2x plus c3 into f3x, then this is known as the linear combination of the function f1x, f2x and f3x. You have studied about the linear combination in the previous unit also. So just for doing more practice, we have another interesting example here, and they are showing, not showing, but they are asking that prove that that this function is a solution of this linear differential equation. This function is also a solution of this linear differential equation, and their linear combination is also a solution. So I am going to do it quickly, even though I have done this, but I want to do this again so that you have sufficient practice. So suppose I am calling the first function as y1. Y1 is e to the power minus x cos 2x, and suppose I have to show that this is a solution of this, means y1 should satisfy this equation. So first of all, I am finding y1 dash. So what is y1 dash? I have to differentiate it. So e to the power minus x first function, derivative of cos 2x is minus 2 sine 2x, right? And then the second function, that is cos 2x, and derivative of e to the power minus x is minus e to the power minus x. Okay, now I find y1 double dash. So I need to differentiate this whole thing. So now here minus 2 is a constant, I take it outside, and then e to the power minus x can again be taken as the first function, and sine 2x as the second function. So I differentiate sine 2x, I will get 2 cos 2x, and plus I take sine 2x as the second function, and I differentiate e to the power minus x, so I will get minus e to the power minus x. So I am done with the first part. What is the second part? Again here we have let me write the term here minus, because it has a minus coefficient. So I write minus can be taken out, and we have the function like e to the power minus x into cos 2x. So I take e to the power minus x as the first function, derivative of cos 2x is minus 2 sine 2x. Okay, and then I take cos 2x as the function and differentiate e to the power minus x, so that is minus e to the power minus x. So if you simplify this, what you will get? You will get here it is minus 2 into 2, so I will get minus 4 e to the power minus x cos 2x, right? And this minus and this minus will become plus, so I will get 2 e to the power minus x sine 2x, and here I will get minus and minus plus, so I will get 2 e to the power minus x sine 2x, and here it is minus and minus plus, so I will get how much? It will be like e to the power minus x cos 2x. Okay, now if you look at this, I think this can be simplified. This term and this term are same, so I am getting minus 3 e to the power minus x cos 2x, and this term and this term are same, so I am getting 2 plus 2 4 e to the power minus x sine 2x. So is it satisfying the original equation? What is the original equation? In place of y we have to put y1, so y1 double dash I am getting is minus 3 e to the power minus x cos 2x, and then plus 4 e to the power minus x sine 2x, right? Then plus 2y dash, so this is your y dash, and I have to multiply it by 2. So here we have minus 2, so if I multiply it by 2, I will get minus 4 e to the power minus x sine 2x, and if I multiply this by 2, I will get minus 2 e to the power minus x cos 2x, and then I have to write 5y. So what is 5y? So plus 5 e to the power minus x cos 2x. So are we getting all 0, or we have made some mistake? Let us verify. So here we have minus 3 e to the power minus x cos 2x and minus 2 e to the power minus x cos 2x. So it is minus 5, and here it is plus 5. So this term and this term is cancelled, and here you can clearly see that 4 e to the power minus x sine 2x and minus for this, it is becoming 0. So what I have just done, I have shown that this is a solution of this linear differential equation. Now the next part I am going to leave for you. What is the next part? That you have to take the another solution, that is y2 is equal to e to the power minus x sine 2x, and you have to show that this is also going to satisfy this linear differential equation the way I have done it. You just have to find y2 dash and y2 double dash, and after that you again have to write the linear combination. So what will be the linear combination? You have to take the linear combination like c1 into the first term, that is y1, so minus e to the power x cos 2x plus c2 e to the power minus x sine 2x, right? So this linear combination will also satisfy this linear differential equation. So please complete this. First verify that this is a solution of this equation, and also verify that this linear combination is also a solution. If I call this suppose y3, then this will also be a solution of this linear differential equation. So this I leave for you to complete. Complete and let me know in the comment section that whether you are able to do it or not. I am moving forward. Now, what do you mean by linear independence and dependence? We also already have studied about linear dependence and independence in our matrix videos, but there we have studied about dependence and independence in context of vectors. Here we are talking about functions. So suppose we have n functions, f1x, f2x, fnx, then these functions are said to be linearly independent on some interval I if the equation, so I am writing a linear combination of this function c1 into f1x plus c2 into f2x plus cn into fnx, and I am putting that equal to 0. If this linear combination implies that c1 is equal to 0, c2 is equal to 0 and cn is equal to 0, then these functions are said to be linearly independent. Otherwise, if some of the values are not 0, then it is known as linearly dependent. So this is just for the definition. We will not be using this to check the linear dependence or independence. We will be using the concept of Wronskian to check the linear dependence and independence. But you should know that what basically it means, right? So let us talk about Wronskian, and this is a very important thing. So listen it very carefully. So let f1x, f2x, fnx be n functions like we have taken in the previous slide. Then how do you define the Wronskian of these functions? We define the Wronskian of this function by Wronskian of f1, f2, fn, and if I call it fw of x, it is defined as a determinant. So what is the determinant that we calculate? In the determinant, we take in the first row, we take all these functions like f1, f2, f3 up to fn. All these functions are taken. In the second row, we take the first order derivative, means f1 prime, second order first order derivative of f2 means f2 dash, first order derivative of f3 that is f3 dash, and first order derivative of fn that is fn dash. In the third row, I write f1 double dash, second order derivative, then f2 double dash, then f3 double dash, and up to fn double dash, right, and so on. So what will be the last row? Take a pause and think that what will be the last row. The last row will be f1. In the second row I am writing the first derivative, in the third row I am writing the second derivative. So in the nth row or the last row I will be writing n minus 1th order derivative. So f1 n minus 1, f2 n minus 1. This is just a way to represent the n minus 1th order derivative. f3 n minus 1 dot 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 up to fn n minus 1. So what we have got is a n cross n determinant. In the n cross n determinant, how many functions are there? N functions. So I am writing them as the first row. In the second row I am differentiating them, writing. Third row I am differentiating them, writing, and in the last row I am differentiating it n minus 1 time and writing. One thing which is important to understand, that Wronskian of n function exists if all the functions like f1, f2, fn are differentiable n minus 1 times on the interval I. If any one or more of the functions are not differentiable, then the Wronskian does not exist. So if I am differentiating something, I am expecting that the derivative exists or the function is differentiable. If the function is not differentiable, then we can't differentiate it, and in that case we can say that the Wronskian does not exist. Right. So once you have calculated the Wronskian, it is very important to note that if Wronskian is equal to 0 in an interval, then the functions are said to be linearly dependent. If you are a 0, you are dependent. If you have watched my linear algebra video, you must have come across this term. That there also, if the vectors are linearly dependent, then their determinant was becoming 0. So if the Wronskian is not equal to 0, then functions are said to be linearly independent. If you are not 0, you are a hero, means you are independent. If you are a 0, you will be dependent on others. Keep this in mind. Now, the first question that I am taking, that prove that these functions are linearly independent on any interval I not containing 0. So how can we prove? We calculate the Wronskian of this three function. And how do you calculate the Wronskian? In the first row, you take the functions like x, x square and x cube. In the second row, you differentiate the function once. So if you differentiate x once, you will get 1, x square will give you 2x, and x cube will give you 3x square. In the third row, you differentiate it again. So you are going to differentiate the second row. So derivative of 1 is 0, derivative of 2x is 2, and derivative of 3x square is 6x. And now I have to find the value. So I am expanding it about the first column. So x into 2x into 6x, that is 12x square, minus 2 into 3x square, that is 6x square. Then minus 1, I am expanding it about the first column. So this column is gone, this row is gone. So x square into 6x, that is 6x cube, minus 2 into x cube, so 2x cube. So what did I get? I got this is 6x square into x, so I got 6x cube minus 6x cube minus 2x cube, that is 4x cube. So we got 2x cube. Now you can see that 2x cube will not be equal to 0 in any interval which does not contain 0. This is important thing to note here, that 2x cube can be 0 also, but 2x cube will be 0 only at x is equal to 0. But if I take an interval which does not contain 0, then 2x cube can never be 0. Right? 2x cube is equal to 0 only when x is equal to 0, but if I take any interval not containing 0, then 2x is not equal to 0 in an interval not containing 0. So if it is not equal to 0, means what? That it is linearly independent. So that these functions are linearly independent in any interval which does not contain 0. It is important. Next question. Suppose we have to show that these functions are linearly independent, and here they have not specified any interval. So how to check that? I am going to calculate the Wronskian. So how do you calculate? There are three functions. So I will get a 3 cross 3 determinant. So I write 1 sin x and cos x, and then I differentiate it again. So I will write 0, derivative of sin is cos x, cos will give me minus sin x, and then I differentiate it again. So 0, cos x will give me minus sin x, and minus sin x will give me minus cos x. So if I expand it about the first column, I will take 1 and I will get minus cos square x, and this will become plus, so it will become minus sin square x. So what we got? We got minus cos square x plus sin square x. So this we know is equal to 1. So we got minus 1, which is not equal to 0. So in the exam sometimes they ask calculate the Wronskian. So we can calculate the Wronskian like this, and since it is not equal to 0, these are linearly independent. Okay. If Wronskian becomes equal to 0, then it becomes linearly dependent. One more question. Examine whether the following functions are linearly independent in the given interval. Right. So there are three functions and we have to check. So how to check? Again I will calculate the Wronskian. There are three functions. The functions are 2x, 6x plus 3 and 3x plus 2. First row. Second row I differentiate them, so 2, 6 and 3, and third row I differentiate them again, so all will become 0. If one row of a determinant is equal to 0, then determinant will be equal to 0. So it is equal to 0 in for all values of x, means it is certainly not linearly independent. So these functions are not linearly independent. Right? independent, because to be linearly independent it should not be equal to 0. So these functions are what? These functions are linearly dependent, LD. So they were asking, examine whether the following functions are linearly independent. The answer is no. These functions are not linearly independent. They are linearly dependent because Wronskian is becoming equal to 0. Okay. So moving ahead, let me take one more example that we have to examine that whether these functions are linearly dependent or independent. So again I am going to calculate the Wronskian. So here the functions are slightly bigger, so we need to be more careful. So how do I evaluate the Wronskian? In the first row I have the functions x square minus x, 3x square plus x plus 1, and then we have 9x square minus x plus 2. Second, I need to differentiate it, so I will get 2x minus 1, I will get here 6x plus 1, and here I will get 18x minus 1, and then I differentiate this, so I get 2, I get 6, and I get 18, right? So I hope up to this there is no doubt. Now to evaluate it, I am expanding it about the first row, so x square minus x, right? And then 18x, 6x means we need to multiply, so 18 into 6, 108x plus 18, and minus 18 into, so this will also be 108x, and minus minus plus 6, right? Then we have minus 3x squared plus x plus 1, and I have to multiply this into this, so 18 into 2, that is 36x minus 18, and minus 18x into 2, so that is equal to 36x, and this minus and minus will become plus, so plus 2. And then we have plus 9x square minus x plus 2, right? And here I will have this into this, so I will get 12x minus 6 and minus 12x minus 2. So you can see that this term and this term is cancelled, this term and this term is cancelled, this term and this term is cancelled. So what did I get here? We get x square minus x into 18 plus 6, that is 24. Here I got 3x square plus x plus 1, and minus 18 and plus 2, so minus 18 and plus 2 will be minus 16, and here we have minus, so let me make it plus, so I write 16, and then plus 9x square minus x plus 2, and this is multiplied by minus 6 and minus 2, that is minus 8. So if we simplify it, what I will get? I will get 24x square minus 24x plus 48x square plus 16x plus 16 minus 9 into 8, that is 72x square plus 8x and minus 16. So you see 24x square and 48x square, 72x square and minus 72. So these terms will get cancelled. Here we have 16x and plus 8x, that is 24x, and here we have minus 24x, so these terms will get cancelled, and here we have 16 and here we have minus 16, so this term will also be cancelled. So what I got is 0. So Wronskian wx is equal to 0. So these functions are what? They are 0 means they are linearly dependent. Let me write it. These functions are linearly dependent. So I hope you have understood the meaning of Wronskian and how to use the Wronskian to decide that whether given set of functions are linearly dependent or independent. Now the next thing I am going to talk about is fundamental solution of the differential equation, or it is also known as the basis, right? So I will explain it through some example. So let us take the first example, that we have to prove that the set of functions forms a basis or the fundamental solution of the equation this, right? So there are two functions x and 1 by x. So suppose I say that first is y1 is equal to x. So first of all I have to check that whether this will satisfy this equation or not, because for this to be a basis solution or fundamental solution, both these functions should satisfy this equation. point number 1. And point number 2 is that they should be linearly independent. How can we check that they are linearly independent? With the help of the Wronskian. So first check whether these two functions are the solution or not. So if I take y1 is equal to x, what is y1 dash? Y1 dash is equal to 1, and what is y1 double dash? That is equal to 0. So if I put it in this equation, what will I get? X square and y1 double dash is 0 plus x y1 dash is equal to 1, and minus, in place of y if I put y1, it is equal to x. So x minus x is equal to 0. So means y1 is equal to x is a solution. If I take y2 is equal to 1 by x, then I need to check whether y2 is equal to x is a solution or not. So I find y2 dash. So what is y2 dash? Differentiation of 1 by x, so that is minus 1 by x square. And what is y2 double dash? So that will give me minus 2 by x cube. I hope you know how to differentiate. It will be x to the power minus 2, so it will become 2 by x cube, right? So whether it will satisfy, so I am checking x square into y2 double dash, so I need to write 2 by x cube plus x into y dash. So what is y2 dash? Y2 dash is minus 1 by x square, and minus y, that is minus 1 by x. So what did I get? From this I will get 2 by x, right? And from this I will get minus 1 by x and minus 1 by x. So I get 0. So it means what? That x is also a solution and 1 by x is also a solution, and this is a second order differential equation. So now if we have got two solutions, next thing we have to check that whether these two solutions are linearly independent. I repeat my argument. My argument is that this is a second order linear differential equation, so it should have two linearly independent solutions. So I have got two solutions, but are they linearly independent? So for that we have to calculate the Wronskian. And how do I calculate the Wronskian? We take the function x and 1 by x as the first row, and because there are just two functions, so it will be a 2 cross 2 determinant. So I differentiate x, I will get 1. I differentiate 1 by x, I will get minus 1 by x square. So if I simplify it, x into minus 1 by x square, that is minus 1 by x, and 1 by x into 1, so that is also minus 1 by x. So I get minus 2 by x, and it is clearly here given that for this differential equation to be normal, the coefficient of highest order term x square should not be equal to 0, means x is not equal to 0. So if x is not equal to 0, then 2x is certainly not equal to 0, means minus 2 by x, not 2x. Minus 2 by x will not be equal to 0, right? So Wronskian is giving me the value minus 2 by x, and it is not equal to 0, means this x and 1 by x are linearly independent. So it means what? It means that this set, the set that is x comma 1 by x, forms a basis or a fundamental solution. I hope you have understood the concept, how to check that whether any given set of functions is a basis or fundamental solution or not. So first of all, we have to check that whether it is satisfying the given differential equation or not. And once we have checked that, next thing that we need to check that whether they are linearly independent or not. So if we have a differential equation of order 2, like it is order 2 differential equation, because the highest order term is y double dash, so the fundamental solution will contain two functions. Let me take one more example to understand this. And this is an interesting example, so you need to understand. I will take some time, and even though the video has become long, but since I want to complete everything, because in the next video I'll be talking about the solution, so this will take care of all the basic requirement. Okay, so the question is so that the set of functions forms a basis of the equation given below, right? So there is an equation given below, and first of all we have to check that this forms a basis. And once we have got that this forms a basis, we have to solve the initial value problem. For the initial value problem, they have given us these conditions. To understand this, because this question contains two part. This question was just having one part, that I have shown that they forms a basis, but after that it is proved that it forms a basis, we also have to solve the initial value problem. So let me solve, and then I will talk about the other aspects of it. So first of all, here there are two functions, and I am calling the first function e to the power x as y1. So I have to show that y1 will satisfy this differential equation. So first of all, to satisfy it, we have to find the derivative of y1. So I will find y1 dash. So derivative of e to the power x is e to the power x, and I also have to find y1 double dash. So y1 double dash is also e to the power x. So if I put it in this equation, I will get what? I will get y1 double dash. So it is e to the power x minus 5y dash. So 5y1 dash will be 5 e to the power x, and plus 4y. So 4y1 is also 4 e to the power x. I am taking, in place of y, I am taking y1, and I am saying that this is a solution. So we can see clearly that this is equal to 0. So y1 is equal to e to the power x is a solution. Anything which satisfies the differential equation is a solution, as simple as that. Now what is the second function that I am taking? It is e to the power 4x. So e to the power 4x should also be a solution. So how do I check? I check y2 dash. y2 dash is how much? 4 into e to the power 4x. And then I check y2 double dash. So that is 16 into e to the power 4x. So whether it is satisfying, if I put y2 dash, it will become y2 double dash minus 5 y2 dash plus 4 y2. So how much is that? y2 double dash is 16 into e to the power 4x minus 5 into y2 dash. So 5 into 4 e to the power 4x, and then plus 4y. So 4 e to the power 4x. So you can clearly see that it is 16 and plus 4 20, and minus 20 is equal to 0. So means this is also y2 is equal to e to the power 4x is a solution. So I have a second order differential equation, and I have got its two solution. Now these two are the solution, but are they basis? So for that we have to check whether they are linearly independent or not. So for that we have to calculate the Wronskian. So how can we calculate the Wronskian? I will take in the first row the two functions, that is e to the power x and e to the power 4x, and in the second row I need to take the derivative. So derivative of e to the power x is e to the power x, and it will be 4 e to the power 4x. So if I solve this, it is 4 into e to the power 5x, e to the power x, e to the power 4x, and minus, if you do this, it will be e to the power 5x. So what I get is 3 e to the power 5x. And you must have heard this earlier also, that exponential function can never be 0. So e to the power 5x can never be 0. So this thing can never be equal to 0. So it means what? That I have shown that these two are solution and they are linearly independent also. So in the next page I am going to continue. So I am saying that e to the power x and e to the power 4x, this forms a basis of the given differential equation. Now once we know the basis, we can write the general solution, and this is important. I am again repeating, this is very important. How do you write the general solution? If you know the basis solution, the general solution is written as a linear combination of the basis solution. So if we have the basis solution as e to the power x and e to the power 4x, the general solution will be c1 e to the power x plus c2 e to the power 4x. And you need to also remember this, that whenever we are solving a differential equation of second order, then its general solution should contain two arbitrary constants c1 and c2. So how did I get this solution? I got this solution by writing a linear combination with the help of the basis solution. But this is not the end of the story, because in the question they are also asking us to solve the initial value problem. Means they have given this condition that y0 and y0 is equal to 2 and y dash 0 is equal to 1. So y0 is equal to 2 and y dash 0 is equal to 1. This condition is given. So if you have this condition, you can use this condition to get the value of C1 and C2, and if you can get the value of C1 and C2, the solution that you will obtain will be called the particular solution. So right now this is what? This is the general solution. And using these two conditions, we have to find its particular solution. So basically, what is y0 is equal to 2? Y0 is equal to 2 means that in this, if I put in place of x0, I will get y is equal to 2. So it is given here that c1 e to the power 0 plus c2 e to the power 4 into 0, so that is also equal to 0. So this is equal to 2. So I get c1 plus c2 is equal to 2, because e to the power 0 and e to the power 0 is equal to 1. And then y dash 0 is equal to 1 is given. So first of all, we have to find y dash. So y dash means, or y dash or y prime, actually the right way to call it is y prime, but I prefer calling it y dash. So if I calculate the derivative with respect to x, I will get c1 e to the power x plus 4c2 e to the power 4x. And now it is given that y dash 0 is equal to 1. So it means what? That in this, if I put x is equal to 0, c1 e to the power 0 and 4c2 e to the power 4 into 0 is also 0. This is equal to 1. So I will get c1 plus 4c2 is equal to 1. So this is the first equation and this is the second equation. I need to solve them. So how can we solve them? We have c1 plus c2 is equal to 2 and we have c1 plus 4c2 is equal to 1. So solving, subtract it. So c1 and c1 cancel, c2 minus 4c2, so I will get minus 3c2, and 2 minus 1 is equal to 1. So I will get what? From this I got c2 is equal to minus 1 by 3. And if c2 is equal to minus 1 by 3, then what is c1? Then c1 will be equal to, from this equation I can write 2 minus c2. So 2 minus minus 1 by 3 means 2 plus 1 by 3. So 2 into 3, 6 plus 1, that is 7 by 3. So the solution will become what? Solution will become c1 is 7 by 3 e to the power x and c2 is minus 1 by 3 e to the power 4x. So this is the solution of the initial value problem, and this is also called the particular solution or particular solution, because we can obtain it with the help of the general solution by using the condition that they have provided us, right? So this is the solution of this question. I hope there is no doubt in it. Yes. So in the last of this video, which is already very long, I am going to talk about something known as Abel's formula. Now Abel's formula gives us a direct process of calculating the Wronskian, and in this process we don't exactly get the actual value of the Wronskian, but we get the similar kind of function. So from that especially we can sense that what kind of Wronskian we are going to get. I am explaining through some example, but before that let us look at this. So suppose we have a second order linear differential equation which looks like a naught x y double dash plus a1 x y dash plus a2 x y is equal to 0, and it is given that a naught x, a1 x and a2 x are continuous on I and a naught x is not equal to 0. Then the Wronskian of this is what is the Wronskian? Basically, when I'm talking about Wronskian for a linear differential equation, so this is a linear differential equation. It will have two basis solution, two solution in its fundamental solution, that is y1 and y2. So if I know y1 and y2, then we can calculate the Wronskian like y1 and y2 and y1 dash and y2 dash. Right, if we know that it has two solution y1 and y2, then we know the formula to calculate the Wronskian. But if we don't have y1 and y2, then also we can calculate the Wronskian. And the formula for this is c into e to the power integration of a1x by a0x dx. So where a1x is the coefficient of the y dash term and a0x is the coefficient of the y double dash terms. For example, suppose I take a differential equation that is x square y double dash plus x y dash and minus y is equal to 0. So this is the same differential equation that I think I have taken earlier here in the previous problem. I think just forget about this, but what I'm giving you is that right now we don't have means we have not studied or we have not learned how to solve this, which we are going to learn in the coming classes, coming videos. But one thing I am giving you here, and this information I am providing you, that its solutions are its bases are x and 1 by x. Yes or no? Basically we have just shown that here in this problem. That is what I was telling, that we have shown that x and 1 by x forms a basis of this. Means we know that x and 1 by x is a solution for this differential equation, right? But what I want to show, that if we know x and 1 by x, then we can certainly calculate the Wronskian. So what will be the Wronskian in this case? That we have x, we have 1 by x, we will differentiate it 1, we will differentiate it 1 by x, that will be minus 1 by x square. So I will get minus 1 by x square into x, that is minus 1 by x, and minus 1 by x, that is minus 2 by x. So this is possible when y1 and y2 are known. But if y1 and y2 are not known, then also we can calculate the Wronskian. And how? So I will take c is a constant, e to the power minus, what is a1x? So here a1x is x, so I take minus x divided by this minus and then x. And what is a0x? A0x is the coefficient of y double dash, so that is equal to x squared dx. So what I get here? I get c e to the power integration of minus 1 by x dx. So I get c e to the power minus log x. So I get c, and e to the power minus log x is basically 1 by x. So we are getting c by x. So did you note that here this is the actual value of the Wronskian, but the Abel's formula is not giving us the actual value, it is giving us the same kind of function, because if I take c is equal to minus 2, I will get the same value of the Wronskian. So this is a limitation, it does not give us the actual value, but it can give us the sense that what kind of function the Wronskian will be. Right. Let me take one more example, like the other example I have taken. That y double dash minus 5y dash and plus 4y is equal to 0. I am talking about this problem, right? This problem, y double dash minus 5y dash plus 4y is equal to 0. And for this I already have shown you that e to the power x and e to the power 4x are the two solutions. So if I calculate the Wronskian in this case using the definition of Wronskian, I will get e to the power x, e to the power 4x, e to the power x, 4 e to the power 4x. And then if I simplify, I will get 4 e to the power 5x minus e to the power 5x. So I will get 3 e to the power 5x. So this is the process of calculating the Wronskian if we know that the solution is this. But if we don't know that solution is this, then what is the formula? That formula is c e to the power minus a1x by a0x dx. So what it will be? It will be c e to the power minus, what is a1x? a1x is minus 5, so I write minus 5. And what is a0x? There is no a0x, means 1, and then I write dx. So it is equal to what? C e to the power, this minus minus becomes plus, I get 5 dx. So the answer will be c e to the power 5x. So again, did you notice that we are getting the same kind of function? Here I was getting e to the power 5x, here also I am getting e to the power 5x, but here we are getting the constant c, and here we are getting the actual value. So the Abel's formula gives us a kind of nature of the function. It does not actually provide me the Wronskian value, but in case if they ask some questions related to this, and if they provide that which of the following is the Wronskian, and it is clear that it will have e to the power 5x terms in it, right? So it can be any multiple of e to the power 5x. The Wronskian using the Abel's formula gives us the information that it can be any multiple of e to the power 5x, right? So this is what I planned for this video, already a long, but if you have watched this video, at least 50% of your content that is there in the unit 2 is already covered. Now only thing that is left is that how to solve the linear differential equation, which is homogeneous with constant coefficient. So that I will be discussing in the next video. So 2 video, the complete units. That's all for this. Share with all your friends and like the video. Subscribe the channel as well. Thanks for watching.